Hi, I'm Jadi and hope you are doing well. In another discussion, I was talking with a friend about the hashes, how to keep passwords, and thought it's good to talk about BCrypt as a very solid and industrially accepted way to keep your password in your database. But let me tell you a little bit about the history. As you know, we all need to keep user password somewhere. So your username is Jadi. The password is 123. This is not a good password, but let's assume. In a very, very novice way, I will have a users table in my database and I will say save Jadi as the user and 123 as the password. What happens here? When the user enters the login page, he will type Jadi in the user, 123 in the password. It will be passed to your backend. Backend will check with the database and says, yes, password and user matches. But what's the problem? When you are hacked, which eventually happens someday, or there is a data leak, all the hackers will see all the passwords. This is ultra bad. Or even your system administrator may want to check and find out about people's password. This is the worst way to go. The next step is creating hashes. As a very quick demo, I can tell import hashlib, and they then say, give me the hashlib dot, for example, MD5, old but generally used way of hashing things. This needs to be, I think, in binary. Yes, it works. And hex digest. Just a very quick. This will give me this hash for 123. Hash MD5 hash of the 123 is always this. So you can save this in your database and say, okay, I have a user which is Jadi and the password is 202CB blah blah. The hash MD5 hash of the password. Now, when I enter into your login page, say Jadi 123, you get this in the backend. Do the same hashing on the provided passwords and check it with this one. So if I have inserted 123, you will get the same thing and you let me to log in. In case of any small divergence, the hash will be completely different. They are different from this. You have this in the database. So now the user can log in because you have Jadi and this, and whatever password he enters, you hash it with the same idea, with the same algorithm, not idea. And if they are the same, you let the user to log in. Very clear and nice. But what's the problem here? You have the user, you have the password hashed, so you have Jadi, and you have 202CB blah blah. If this database leaks, which eventually happens somewhere, someone may try to find what the actual password is. It's very easy. They can create a hash of 1. It will be something. Create a hash of 2. It will be something. 3, 4, A, B, AA, 1, 1, 1, 2, 3. Boom. This will be the same with this one, and they will know that your password was 1, 2, 3. This is called brute forcing. And there are better ways. If I have this, I don't even need to brute force it. I can go to sites like Rainbow Attack. There is a very famous site, which I don't remember the name, Rainbow Attack online site. And we have the crack station, the most famous one. What is rainbow attack? Someone, when having extra time, was just trying every possible password and saving their hash, different hashes. Now we were working with MD5, but there is also SHA or SHA-1, SHA-256 and other methods. They were hashing whatever they could and saving the hashes in a database. So now I can only give them a hash. If they have it in the database, they will show me what it was. So we can just say, I'm not a robot, hopefully, and crack this hash. It says, I have seen already this hash. This is an MD5 and the result was 123. Very easy. So our way of saving the users and their MD5 hashes does not work that well. Next step is adding a salt. You can say, okay, on my site, I have funky punky AB2 or a random string. Whenever a user enters a hash, enter a password, so 123, you say, okay, I will add this funky punky ABC, AB2, whatever it was, to the end of this, and then we'll hash this and we'll save the result in the database. That would be the hash of 123 funky punky ABC. This will be the result. I will save this one in my database. Then when user is logging in, I will ask for the password. We'll add the same salt to the end and we'll hash this. The good point is, for sure, this is not in the any rainbow table, and if someone wants to, and if he wants to try to break it, it's very long, so it will take a lot and lots and lots of time, which is, what I did. We had to try this one. And it will take ages for them to be able to brute force this. Bicycles, the question is this the bicycle? Sorry if you guys crash somewhere, because I was not sure if that was the bicycle or not. It cannot crack it because this is unknown. Never ever they reached this when they were creating a rainbow table of everything. This is too long. This is called adding a salt. What's the problem here? You have one user with the hash, with the salt user, so you added the funky punky ABC to the password and created the hash and did all the same. Now someone wants to attack and crack this. What they can do, they can create their own rainbow table. So they can, if they know this can be in the database somewhere, in your file system, in your memory. If they can find this and know your algorithm, they create their own. So they create one funky punky ABC. The hash will be this. 2 funky punky ABC. The hash will be this. A, the hash will be this. A, and as long as they can go, they will continue creating a rainbow table and then check if this is here. If this is here, it was A funky punky ABC. So the password was A. This is another problem. Next step is having a salt and a pepper. When you enter a hash, in their database, they say, okay, user is Jody. You say my password is 123. They add funky punky ABC and they add some random string from here, like salt. Salt is something. So they add that something here. They will hash this and save the result in the password. This is very cool because now if you want to do a rainbow attack and if you know this pepper and salt, this comes from operating system, environment variables, a file, in memory or whatever, and this salt is here. So in this case, or the salt can be user ID or anything special for this user which doesn't change. Now when the user logs in, if they say my password is 123, the system will add this pepper, funky punky thing, then add this salt, then hash all of this and checks it with this one. If it's correct, it works. Now, even if the hackers find out about this and know about your pepper, they can create a rainbow table only and only for this specific user. Because the next user, for example, Joe, will have a different salt. So the rainbow table for this user won't be useful here. So even if they spend time create specific rainbow table, know your algorithm, know the pepper, know the salt, they can create after a long time a rainbow table only for this user. Cannot be for this one. Cannot be used for this one. So this is why you can combine salt and pepper. But still you can make it better. One of the very well-known algorithms is the BCrypt. It's an industrial proof. Many different systems. For example, Laravel uses this by default, and it has very, very cool idea. If you want to use it, you have to install it in Python. So pip install BCrypt. If you are having a problem here, please make sure that you might be installing for different versions. For example, in my system, I have to go with pip3 install BCrypt. Again, it won't work because when I'm running the IPython is using Python 3.9 and not 3.11. So I have to go with pip 3.9 install BCrypt. Now this version of Python has the BCrypt. Then I will go into IPython 3. What I do is I will import. Now that I have BCrypt, I can start hashing things using BCrypt. BCrypt uses salt and your password to create a hash. So you have to create the salt first, then provide the password you have, and it will provide you a hash which you can save in your database. Let's go for it. I say my salt equals BCrypt gen salt, generate the salt. If you do a die run BCrypt, you can see that it has very few functions other than these normal ones. It has check password, generate salt, hash password, and one for the key, which we don't use at the moment. So I created a salt. This is my salt. It's a binary string. We will see the sections later, but at the moment we have a salt. Then I can say BCrypt hash password. My password, it should be in binary. So if it's 1, 2, 3, and I have to provide my salt. It takes a little bit of time. This is important. And it creates a new string in binary. Now it's enough for me to save this in my database. And then when a user provides a new password and I want to check if it's correct or not, I can say BCrypt check password, the newly provided password, which was 1, 2, 3, with this binary string or array or whatever you call it. It says, oh, it's true. If the password is wrong, any difference, anything, it will say false. So what happened? First, we created a salt. Now the salt is different because I've created a new one. Then we said hash this password using this salt. It gave me this, and it's enough for you to save this in your database. This is base 64, so it's all normal ASCII characters, nothing string. You can save this in your database. Later, whenever a user provides a password and you want to check if the password is correct, you can ask BCrypt to check it. So we can say BCrypt check password B1 to 3 is provided, and this is what I had from previous sessions. And it says true. This works for this password. But the fun part starts here. This thing, which is the result of hashing a password with a specific salt, has different sections. First, it has this one, $2B, separated by dollar. So you have 1 2B here, you have 11 here, and you have something else. 1 2B indicates the algorithm used in creating this hash. 12 is a very cool concept called cost. You can make creating these hashes costly. This can cost your CPU. That's why it took a little bit of time to create this hash. We'll talk about this later. This is one of the geniuses behind the BCrypt. And then, strangely again, so this was your algorithm, this was your cost, this was your algorithm, this was your cost, and this was your salt, actual salt. So these two were inside your salt. JDL blah blah T3E. JDL blah blah T3E. So your salt is also here. And this is the actual hash resulted from your password, your algorithm, the cost you decided to have, and this. That's why you can do a check password on this one. Because you have the algorithm, you have the cost, you have the exact salt used, so it can check if this is generated again or not. This is very fun. But let's have a look at the actual algorithm of BCrypt. This comes from the old days in OpenBSD world. The first one is the algorithm. Here we had 2B. It fixes a bug in 2A. In old times, this used to be $1. Normal MD5 based crypt. $2 is a BCrypt based algorithm. That's why BCrypt. BCrypt based. And 2B is a newer one which fixes one bug which was found in the original OpenBSD implementation of BCrypt. But what's the algorithm and what's that cute cost? The BCrypt algorithm works like this. It gets 3 inputs, cost, salt, and password, and outputs a hash in the format you just saw. First, it uses BCrypt or another improved and slower down BCrypt. This is very, very nice. The idea that they made BCrypt more CPU hungry and slower with your password, with your salt, and with your code. It creates some kind of a key. Then uses the ECB known encrypting algorithm to encrypt a known string. Orphan, beholder, scry, doubt. Total nonsense. Just 4 random characters. If you are looking at it very closely, open BSD. Cool. So it works kind of vice versa. It creates a key using the BCrypt setup algorithm, using your password. So it creates a key and then uses that key, P and S, to encrypt a known phrase 64 times. And this is what creates the last part of whole thing, your hash. So what happened? You provided a salt, your password, and a cost, which is normally 12. And it used this string, well-known string. Default is this, and always it is this if you are using BCrypt. And for 64 times encrypted using the ECB, using the key generated by your password with a slowed down BCrypt. So your password created a key, and for 64 times this phrase was encrypted, and then you had that specific Oh, hash. Interesting. Why is this cost? Normally, if I want to break this, I can say, okay, I have seen this in the database, and I have seen this in the database, and now I want to break it. Let's try 1. 1 was not correct. Let's try 2. 2 was not correct. Normally, a computer should be able, or at least in our mind, will be able to test thousands of tests every second. But this is slowed down using that cost. When I was creating my salt, which is 12 by default, and using it to create this, practically that 12 slowed down the system to the factor of 2 to the power of 12. If I was using the cost 13, it would be twice as slow. 14, 4 times as slow. 15, 8 times as slow, because it's a power of 2. So if I create a new salt and say my new salt is BCrypt generate salt, and my rounds should be 15. It used to be 2 to the power of 12. Now it's 2 to the power of 15. 3 differences. So 2 to the power of 3 times slower, which is 8 times slower. It created this salt. My new salt is this. Now I can say BCrypt hash my password B123 with the salt I just created. You can see it's 8 times slower than the previous time. If I would go with salts with 17, wow, 4 times slower than the previous time. So, oh my god, this is so slow. Now, I will save this in my database. It says this is the algorithm, so it's EksBlowfish. This is the cost, so it's very costly. This is the key up to somewhere, salt, and this is the hash. Now, if I want to check password, if it's correct or not, I should say BCrypt check password 1, 2 with the no salt. 1, 2, what I did with this. Right? Yes. This is the new password, and this is what I had in my database. It takes the same time to try. So it's super slow. It's kind of impossible to do the checking. Right? To do the, brute forcing, trying every possible password to find out. This is how people love BCrypt. You can play with this every time computers progress. You know the Moore's law. Every 18 months, computer power, kind of nowadays, doubles. So after every 18 months, in your program, you just add 1 to your round. Will it affect the older passwords? No, because your database is saving the rounds for this specific calculation. And when you are saying to check, you are saying check this password with this one. So if you change the algorithm, if a better algorithm comes, if you found a bug here, maybe after 3 years we are using 2C, or we may be able to use something even newer, whatever, but still your lovely BCrypt will work. Because this will change to a new algorithm. You can increase this every few years to something more, and depending on how much processing power you have, find something cool. Now for sure 17 is not good on my computer because it takes too long. If a user wants to log in, it's too much wait. Maybe in my case, for example, something like 14 looks cool. Still a little bit slow, but if it's only one user, it's acceptable. If I have thousands of users, this is too slow. But again, you can find the correct number on your own computer and increase it after a while. The cool point, as I said, is now this specific user, if you are saving this, now the 14 is here. So your cost is here. You can increase the cost when new computers are coming, higher processing power is coming. You want to prevent people from brute forcing and whatever. That's how the cost works. And as you saw, another fun thing was we create a key based on the password, and then we encrypt this specific string using the key created by the password. This was very, very, very nice. And this is how this EksBlowfish, slowed down blowfish, works. It's for extensive blah, 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 blah. Let me see, what is it? Blowfish EKS, expensive key schedule blowfish. And how it works is like this. It creates some things. It's a little bit more complicated. It creates sub passwords, sub keys, and this kind of stuff, but it repeats for 2 to the power of cost. So when you increase the cost, time for preparation doubles. This is so cool. There are also some negative points. For example, if you want something newer, you can check this Argon 2. But there is a maximum password length. So you can only use the 72-byte password. In many implementations, if you have a longer password, your password will be truncated. A way for preventing this is first doing a hash on your password. So you have a string like MD5 and then go for based on that one. And also the base64 encoding is not standard, at least not based on the RFC. It's kind of different, which is not very nice, but historically we will keep it as it is. BCrypt Python, you can go check the source, it's fun. I've just found out that it's in Rust and not C anymore, because practically they were using the older codes from OpenBSD. But this BCrypt library now is in Rust, as you can see. It uses BCrypt Rust. It's like this. And that's it. Hope you have fun. These are all the things I wanted to tell you. You can play with it. Sorry if it was a little bit confusing. If you are still here and you are confused, this is the best news. It means you are going to be a professional. Because if nothing is confusing for you, it means you knew all of this and okay, just go. Go for it. If it's super confusing and you are not continuing watching it, it means okay, it was too high for you. Or I was too bad. Anyway, glad that you are here. Thank you and hope you enjoyed.